Hello, my name is Leo. Today I'm going to introduce a paper, very interesting paper, called Dynamic Routing Between Capsules. So CNN is very popular nowadays. However, something is wrong with it, according to Hinton. For example, it will have some difficulty in generalizing to novel viewpoints. And that is one of the motivations of proposing Capsulenet. Hinton has listed 4 arguments against pooling. The first one is it is a bad fit to the psychology of shape perception because it does not explain why we assign intrinsic coordinate frames to objects. And the second one is it solves the wrong problem because we want equivariance instead of invariance. Equivariance is when the property of the object changes, the property of its representation should change in the same way. The third one is it fails to use the underlying linear structure. We want a face like this, not a face like this. The last one is pooling is a poor way to do dynamic routing, because finding the best routing is equivalent to parsing the image. Voila, here we have the structure of dynamic routing between capsules, the Capsulenet. The input is 28 by 28 one-channel image from MINIST, and the first layer is the normal convolution layer with ReLU, which is outputs 256 dimension, a channel, like. And the second layer is called primary caps. There are 32 capsules. Each capsule is organized with 8 neurons. And last layer is there are 10 capsules. Each capsule outputs a 16-dimensional vector. And I found online the structure which can help us to understand the Capsulenet easier. So the first layer is normal conv layer with 256 channels, and we can see that the output is scalar, and then we pass it through ReLU for nonlinearity, and then it's 32 capsules. You can see that here the output of the capsule is vector instead of scalar, so we need a new nonlinearity function which can work with vectors. In this paper, they proposed to use squash function. Squash function is an easy function which just adds some non-linearity, and they keep the orientation, the direction of the vector, and they shrink the length of the vector to less than 1. And the last layer is digit caps. It's 10 capsule, and each capsule will output a 16-dimension vector. And between the primary caps and digit caps, there's a process called dynamic routing with agreement. So, how this network can deal with the 4 problems with pooling we presented before? Firstly, the vectorized output here and here. So it can be seen as a coordinate frame, which will include the information like location, orientation, texture, etc. And the length of the vector is the probability that this entity exists or not. And equivariance part is here. There are 2 kind of equivariance Hinton introduced: place-coded and rate-coded. So in the lower part, when it changes a lot, it will be place-coded because it will activate different neurons. But when it changes a little bit, it will be the same neurons, but the output of the neuron will change. So in this case, for the lower part of the network, the equivariance will be place-coded. But for the higher part of the network, because the reception field is, the domain is bigger, so the place-coded equivariance will be converted to rate-coded equivariance. About the underlying structure, linear structure we've talked about. Here they added the transform matrix between different capsules. And these matrices can will obtain this information of transformation or include the information of underlying linear structure. And the last part is about routing. Here they propose a dynamic routing process to replace pooling. So now we have all the ideas how they propose it and how it's used, and let's take a look how they are realized in real experiment. Firstly, capsule. The objective is to group neurons in each layer into capsules that do a lot of internal computation and then output a compact result. It's like binding together some information to form a coordinate frame. The activities of the neurons within an active capsule represent the various properties of a particular entity that is present in the image, like position, size, orientation, deformation, etc. And the overall length of the vector of instantiation parameters represents the existence of the entity. And fourth, the orientation of the vector to represent the properties of the entity. So where this idea is from? Actually, it's from computer graphics. Graphics programs use hierarchical models in which spatial structure is modeled by matrices that represent the transformation from a coordinate frame embedded in a whole and to a coordinate frame embedded in each part. So capsules are responsible to find the coordinate frame, like embedded in the whole or embedded in each part. And then we need to find the spatial structure that is modeled by matrices. That is these transform matrices during the process of dynamic routing. So these matrices connect each capsule output between these two layers, the primary caps and digicaps. So there are in total 1152 by 10 matrices, which is learned from backpropagation. And as we have all the material now, but how these are connected is called routing by agreement. So firstly, we initialize the weight, because here every capsule, every connection will have weight. Here we initial the weight, and then we use softmax to normalize the weights. And then, very important part here. So UI is the output of the primary caps, so 8-dimensional vector. And Wij is a transform matrix between the output I, capsule I, and capsule J. Capsule I from primary caps, capsule J from the digit caps. And then this will produce a prediction called U hat based on I and J, connection I and J. And then you calculate the output with the weighted output, as a weighted prediction weighted sum of predictions. And then we use squash function to add nonlinearity. So the Vj is actually the output of digit caps. So now that we have the output of digit caps, and we have the prediction of each connection, for each output, how we update the weight is easy, because these are two vectors. We just do a multiply by two vectors. If these two vectors has similar direction or orientation, this part will be positive, which means that the prediction of UI agrees with the output. So the weight of this prediction will be increased. Otherwise, the weight of this this connection weight of this prediction will be decreased. We have an example here to show how it works. So here, this line is the primary caps, and this line is digit caps. So for primary caps, we will detect entities. For example, this capsule, he detects a mouse like this, with this direction. And by multiply with the transform matrix, it should have a prediction like a head like this with this direction. And here, if we have a nose like this, he will do a prediction like this. So these two predictions are very different. Imagine if we have a third capsule like this and did a prediction like this. So these two capsules agrees with each other and disagrees with this capsule result. So the weight of these two capsules connected to J will be increased, and the weight with this prediction, the connection between these two capsules, will be decreased. This is a dynamic routing with agreement. And actually, in the Hinton's presentation, he proposed to use a mixture of a Gaussian and a uniform to detect the agreement. And I don't know why in the paper they use the vectors multiplication. So maybe we can try this too, maybe to find out which one is better. So after the classification part, they added reconstruction part, because it can boost the routing performance by enforcing the pose encoding in the capsule vector, because the output is a 16-dimensional capsule vector, and from this vector they're going to reconstruct the image, and then they're going to, which means that in this vector you should have all those information like rotation, location, orientation, etc. So that's how it can enforce the pose information in the capsule vector. As we can see that there are two parts of the training, so there are two loss also. The first is margin loss of digit existence. It's a very simple loss. If this digit exists, presents, if this is a correct digit, the length of the output vector should be over than 0.9. Otherwise, it should be shorter than 0.1. And here lambda is equal to 0.5. And the second part of the loss is the reconstruction. So it's the sum of squared differences, the Euclidean distance between the two images. And they multiply this loss by 0.0005 so that it does not dominate the margin loss during training. So here are some results. Keep in mind that the aim of this paper is not to explore the whole space, just simply to show that one fairly straightforward implementation works well, and that dynamic routing helps. So here we can see some magic. It is sum of the 16 dimensions, and they try to trick the number by 0.05, test 11 different numbers. And we can see that, for example, here, this dimension, it represents the scale and thickness. And this dimension, it represents the localized skew, which means that, yeah, it works, right? And there is some results about reconstruction. For example, this one we can see that it does not only reconstruct the number, it also filters the noise from the original image. It's very nice result. However, it only has very good results on MNIST, not really on very bigger or more complex data sets. However, I think there's a lot of very inspiring part in this paper. For example, the definition of capsule. So change the scalar output to vector output, and enforce the information like entity, the pose orientation in the vector. It's kind of coordinate frame conception. And then it is kind of viewpoint invariant by adding all these transform matrices, which will encode the underlying linear structure information, which is also magic. And the third one is the dynamic routing to activate different neurons, which is, evidently more intelligent way than pooling. What can be done? A lot. For example, the nonlinearity function, the Scotch function, can be changed to improve the performance. The dynamic routing process can be improved too, like Hinton originally proposed to use a mixture model, and in this paper is kind of an easy dynamic routing process. And also, I'll be very interested in what is the effect of vector size. Like they chose 8 dimensions for the primary vector in this paper, and 16 dimensions for the digit capsules. Does this vector size, vector dimension affects a lot or not? And also the last one is how to implement this conception to more complex data like ImageNet data. It's still an open question. And here there's a code for TensorFlow implementation, which can also help us understand better about this paper. And thank you for your attention. Hope to see you next time.